Slope vector is a set of values that represent the polarization state. The first value is the total intensity, and the other three values are the difference between the linear, horizontal, and vertical, linear plus and minus 45 degrees, and left-handed and right-handed circularly polarized light. The degree of polarization can be described using these equations. And the point here sphere is a visual representative that describes a fully polarized light. The equators represent the linearly polarized light. The north hemisphere is right elliptically polarized, while the north pole is right circularly polarized. And the south hemisphere would just be the opposite.
Pneumatic liquid crystals have two characteristics that we take advantage of. The first is that even though they have no positional order, they tend to point in the same direction. The second is that the refractive index is different along separate axes. When you place these crystals in between two electrodes with no voltage, they'll align and create a very anisotropic source. When you run a voltage across these, they will cause the crystals to unalign and produce an anisotropic source.
In this lab, we use an axiometric polarimeter to measure the properties of a liquid crystal cell. So a polarimeter consists of a polarization state generator and a polarization state analyzer. Since the polarimeter uses white light as a source, we need to insert different filter to change the operating wavelength. And the linear retarder inside the polarization state generator is essentially a quarter wave plate, which is wavelength dependent. So that's why we need to calibrate the system every time when we change the wavelength. After the system is calibrated, we then apply a plus and minus 1 volt square wave at 2 kilohertz to the LCC. Then we record the retardance magnitude and the rotation as we slightly increase the peak-to-peak voltage from the function generator.
Here you can see the results from the axiometer measurements. As you can see, our 532 measurement had an increasing slope, which means we were likely in an area that had to be rectified, and once rectified we got the expected downward slope that we wanted. In our 633 we have very weird spikes and decreases. The rectified wouldn't change that, so they both look kind of the same. This could mean that they are in an area that, so we expect the mirror of this image, and at the top of this could curve off, and we could have gotten measurements in that area, which would have caused the weird spikiness. And our 532 measurements we expect to be in one of these areas because we had an increasing slope when we expected a decreasing slope. Here are the graphs of our half wave plate measurements.
For this part of the lab, to determine the orientation of the first polarizer, we put in a polarizing beam splitter, and when no beams coming out, we know that the polarization state of the first polarizer is vertical to the propagation axis. Then we rotate the second polarizer to 90 degrees, so now those two polarizers are crossed.
Here's our intensity transmission for our LCC intensity modulator. For this, we saw an initial increase and then a decay as our voltage increased. For this, our first polarizer was set to 45 degrees, our LC cell with its fast axis set at 90 degrees, and the second polarizer set at 135 degrees. Here we have an output of the power transmission. This is when we rotated our polarizer to get the output that was on the detector. Next, we have our LCC polarization rotator with our linear polarizer at 0 degrees, our LC cell with a fast axis at 45 degrees, our quarter wave plate at its fast axis with 0 degrees, and our last linear polarizer at 0 degrees. Here was our output. And lastly, we have our LCC variable beam splitter. This is our voltage against our transmitted and reflected beams from the beam splitter. For this, we saw that the ratio increased as our voltage increased.